Hello everyone, welcome to the channel. Today we are going to discuss on the topic about high lift devices, which come under the course of low speed aerodynamics, which will be studied by the BTech second year aeronautical engineering students. Myself, Arun Nema, working as an assistant professor in the Department of Aeronautical Engineering at Bharat Institute of Science and Technology, Institute of Higher Education Research, Chennai. So today we are going to discuss about high lift devices. So high lift devices are very useful, and they are mostly used for generating the high lift. Suppose a cargo aircraft is there or a heavy jumbo jet is there, which require more power and more lift to carry over the loads or fuselage or the weight of the aircrafts. So for that purpose, we are using the high lift devices. So in high lift devices, mostly we use in the wings. We will be keeping the flaps, slats, and slots. So they are generally located at the leading edge or trailing edge of the wings. If we go to the scheme of presentation, so in scheme of presentation, first I'm going to explain about the purpose of high lift devices, then flaps. In flaps, there are different parts are there. First one is trailing edge flaps, in that plain flaps, split flaps, slotted and multiple slotted flaps, follower flaps, comparison of trailing edge flaps, coefficient of lift max and stalling angles, drag, lift drag ratio, pitching and center of pressure moment, change of downwash, overall pitch changes, aircraft entry with flaps lower. This is under the trailing edge flaps. If you go to the leading edge high lift devices, so there Kruger flaps will come, variable camber will come, leading edge flaps, effects of the leading edge flaps on lift, leading edge slots and flats, automatic slots, disadvantage of slots, drag and pitching movement. These are two types under the flaps. Then trailing edge plus leading edge devices together, sequence of operations, asymmetric of high lift devices, flaps, load relief systems, choice of flaps, setting for takeoff and climb, management of high lift devices. Under that, flaps, retraction after takeoff, and flaps extension before landing. So these are the you can say the topics which I'm going to discuss. Then next one we will move on to the purpose of flight devices. So purpose of flight devices, it's the main function is to reduce takeoff and landing distance. If we have a short runway, then we can use the more high lift devices, extendable flaps and slots, so which will generate a lift in a short runway. So it will be very useful. Suppose some places, if a big aircraft or cargo aircraft is there, it's require a bigger runway. So if we have short runway means there also it can land and it can take off. Reduction in stalling speeds. So as I told you in the previous lectures that if we keep on increasing the angle of attack, then after some point of angle of attack, the lift separation will happen and the stalling can happen. So in that way, plane can get crash also. So third one is lift augmentation by increase in camber and lift aspects. So camber, if you go to the previous of my lecture, in that you will find aerofoil nomenclature. In that I define the leading edge is the starting of the airfoil, trailing edge is the end of the airfoil, and then camber line, mean camber line, angle of attack, camber. So we have there the maximum distance between upper and lower surface is called as camber, and then their upper surface is there, lower surface is there. So many other things also there in that. So flaps mostly what they call as a hinge portion of a leading and trailing edge of the wing. Okay, so the extra portion. Then if mostly in low speed aircraft, they'll be used at trailing edge, and the high speed aircraft they'll be used leading and trailing edge both. So this is the trailing edge flaps. So it's which is mostly used in the low speed of aircraft. So if we talk about plain flaps, as you can see in the figure, there is not much changes. Okay, only the slight the last part is there, which is just lowered. So this kind of flaps is very simple to construct, and it increase the coefficient of lift max, which also will generate high drag, mainly used on low speed aircrafts. Okay. Then this is the CL max, coefficient min max, and stalling angle. So what will happening, like if we use the effective angle of attack, which you can see in the figure which is generated in over here, this will affect the reduction of angle of attack on basic sections, because we know that if we keep on increasing angle of attack, stalling can happen. So if we use these flaps, it can uh, reduce the angle of attack. And second one is split flaps. So split flaps is similar to the plain flaps, but it can be go retracted and lowered also. So the flap forms part of the lower surface of the wing trailing edge, the upper surface contour being unaffected when the flap is lower. So as you can see in the figure, only the down part is lower, the upper part is as it is. So the split flap caps about the same increase in lift as the plain flap at low angle of attack, but gives slightly more at higher angles, as the upper surface camber is not increased and so separation is delayed. So the drag, however, is higher than for the plain flap, but it increases the depth of the wake. So as you can see that this flaps also give the same kind of lift which can be given by the plain flaps, but it having a drag also. Okay, then the third, slotted and multiple slotted flaps. So as you can see in the figure, we can see the two or three slotted flaps. So in this way, it can increase the more surface of the area, it can generate more lift. So the purpose of the slot is to direct higher pressure air from the lower surface over the flap and re-energize the boundary layer. So this will be re-energizing the boundary layer, because if boundary layer gets separated, then the lift will be separation and stalling, and then crash can be happening. To avoid that, they'll be using the slotted and multiple slotted flaps. This delay the separation of the airflow on the upper surface of the flap. The slotted flap gives a bigger increase in CL max, okay, than the plain or split pad, and much less drag. That is a more complex construction. So as you can see in the figure itself, it having a different multiple slotted flaps. It is difficult to construct, increase the cost also, but it gives more lift compared to the split and plain flaps and generate a less drag. Then we can go to the FOWLER flaps and FOWLER flaps, slotted FOWLER flaps. So as you can see in this figure of the aerofoil, you can see that the upper surface is not changing, on the lower surface is completely coming up. So the first one will be the single, or you can say FOWLER flap, and the second one is triple slotted FOWLER flap. So having a three types of slotted. So the construction will be difficult, but it will generate more number of lift. So what exactly is given? Because of the combined effect of increase in camber and surface area, the FOWLER flaps give the greatest increase in lift. It gives least drag because of the slots and reduction in thickness. So this is double advantages. It gives more lift and least drag because of the surface area and camber will increases, and because of the slots reduction in thickness correlation. However, the change in pitching moment is greatest. Guess why? Because it could be the reward extension of the chord. Okay, so this is the reason. Then this is the comparison of trailing edge flaps, as we have seen it: plain flap, plain split flaps, slotted flaps, and FOWLER flaps. So as you can see in the graph, the graph between coefficient of lift and angle of attack. As you can see in the basic section, we have less angle of attack. Okay, but we have a less coefficient of lift. But as you can see that if we move on to the plain flap, split flap, and slotted flap, they having almost in the positive manner same angle of attack, but they giving more coefficient of lift. Even they having a negative value of angle of attack, they are generating the more coefficient of lift because the help of the flaps. Okay, then next to the increase in drag due to trailing edge flaps. So as we have seen it, the drag also increasing. So there is a graph between coefficient of lift and coefficient of drag. So as you can see that coefficient of lift also increasing, so coefficient of drag also increasing. Okay, so the basic section having a less CL value and having a less CD value. But if you see the FOWLER flaps, it having a more CL value and having more drag also, more coefficient of drag also. As compared to split and plain, they almost same, but slotted and FOWLER having a more number of coefficient of lift and also having a more coefficient of drag, but that also increasing up to certain limit, as you can see in the graph. After some time it's getting constant and then decreasing. Then lift to drag ratio. So this is one of the most important factors, because lift by drag means lift value should be more. So the ratio should be always more than 1. It will be very beneficial for the aircraft, because we require more lift compared to the drag. At the time of takeoff also, the more number of lift is required. So as you can see the graph, CL and CD, coefficient of lift and coefficient of drag, you can see two figures. So first one is like a basic sections, and the second one is there. So there is an angle between that creating it. So as you can see that the black one having a more coefficient of lift and also the more coefficient of drag. But after certain time, it's getting constant and getting reduced. Okay, then we will talk about the pitching movement. Okay, so pitching movement and center of pressure movement. So flap extension will cause center of pressure to move aft, thus pitching the aircraft nose down. So as I told in the previous class, we also having other control surfaces and we also having a part of the plane in tail parts, horizontal and vertical stabilizer. There also radars are there, which will change the direction of the aircraft, and elevators also there, which will help to move the aircraft nose up and down. But we also use the flaps to do that thing. So here flaps extension will cause the coefficient of pressure to move aft, thus pushing the aircraft nose down, and then flaps retraction will move the center of pressure forward, thus pushing the aircraft nose up. So with the help of flaps also, we can move the aircraft nose down and nose up also. Then change of downwash. So downwash effect also will come here. So tail plane effective angle of attach is determined by the downwash of the wing. So you can get the effective angle of attach, okay, determined by the downwash of tail. The lowering flaps increases downwash, thus decreasing tail plane angle of attack. So if we opening the flaps, that will increase the downwash, but that also decrease the tail plane angle of attack. And this is known as pitching. This is one good advantage. We can see things in next figure. Okay, so as you can see in the figure here, the first figure we'll be talking about seeing here in the wing. So you can see the center of pressure at half the wing. So because of that, the nose down will happen it. And as you can see in the right side, the tail plane is there, where downward effects is reducing it. Okay, and then if you see the left side down figure, which is nose down pitching movement, as you can see that center of pressure had moved forward. So because of that reason, that happening it. And then right side, you can see the increase in downwash. So nose up pitching movement. Then overall attitude when lowering the flaps, what exactly happening in overall summary. Like it's a kind of a conclusion point with the help of lowering the flaps. So when the flaps are lower, the lift force increases as the value of CL increases, because the surface area will increase, so CL value will increase. CL is the coefficient of lift, so lift automatically will increase. So when the flaps are lower, the airplane starts to climb. To arrest this, the value of CL has to be lowered by decreasing the angle of attack, which is done by lowering the nose down. So what happening when the aircraft is climbing it? If we use the flaps, we can get the more CL value, so the more lift will be there. At the same time, by using the flaps, we can reduce the angle of attack. How we will do that? By lowering the nose down. As we move on to the leading edge of higher devices, so in the leading edge higher devices, there are two types of flaps are there: leading edge flaps and leading edge slats and slots. So leading edge flaps. So what exactly leading edge flaps are doing? They increase the camber of the leading edge. So these are on leading edge, so they increase the camber of the leading edge, which will increase the coefficient of lift, which will increase the lift of that. So one of them is Kruger flaps. So one of them is Kruger flaps. So you can see as in the figure in the first and second figure, one is retracting and the second one is extending. So they are at lower surface of wing leading edge, wrote about their forward edges shown in the figure. So one will be moving forward, one will be coming backward. Then second one, you can see this, the variable camber leading edge. Okay, so the first one is extended and the second one is retracted. So they give better efficiency than Kruger flaps by giving better leading edge profile. So these kind of flaps will give better efficiency compared to the previous one, Kruger flaps. Thus, to promote root stall first, Kruger flaps are used inward and variable camber flaps are used outward. So where they are using it, they have clearly told that. So where the Kruger flaps are used in inward and the variable camber flaps are used in outward. Then the effect of leading edge flaps on lift test, as we see in the previously the trailing edge flaps, how they're affecting on lift. Now we're going to see here the effect of leading edge flaps on lift. So as you can see here, the graph between coefficient of lift and angle of attack. The basic wing section, as you can see that they're having less angle of attack and less coefficient of lift value. But if you see the with leading edge flap, the coefficient of lift value also increasing and the angle of attack also increasing. Now we will talk about the leading edge slots. Okay, so we have seen flaps, we have seen trailing edge flaps, we have seen leading edge flaps. Now we're going to see the leading edge slots. So as you can see in the first figure, there is the flow is coming from the forward direction, and then when the back is going is completely so many vortices and the turbulence is generating. So as the coefficient of lift max value, wing is there. So giving an adverse pressure gradient. As you can see in the right side figure, we have a slats. So what happened? The flow was gone smoothly. Slat open and boundary layer re-energized. Okay, so if we use slats, we can extend it and then the boundary layer will be energized. Boundary layer will be energized means it will help to delay the flow separations and the more number of lift will be generated. So as we can see here in the definition, it's the gap between the lower and upper surface of the leading edge of the wing. So this is mostly using the leading edge of the wing. So it is a gap between the lower and upper surface of the leading edge. It could be a fixed or moving part. So it can be a fixed or it can be a moving part. Both kind of we can use it as slat. So when slats are employed, they re-energize the boundary layer. So as we can see in the right side of the figure, so when we use a slat, it will re-energize the boundary. So here the effect of slats and slots on the lift. So as we can see in the graph between coefficient of lift and angle of attack on the left side, you can see the coefficient of lift value is 0.5, 1.0, 1.5 and 2. And as you can see the down the angle of attack, the value is 5 degree, 10 degree, 15 degree, 22, 25, 30 degree. So as you can see that in two figures are there, one with respect to the wing and one is the wing plus slats. So you can see the wing plus slats increasing both the things. It also increasing the coefficient of lift and it's also increasing the angle of attack. So having both the advantages. So after certain limit they will increase and then decreases. So as you can see in the figure, right side one, there is no slat and this with slat. So you can see that how the variations are there without slat. So if you open the slats, so the boundary layer will be re-energized. Then some of the aircrafts will be using the automatic slats. So most of the control surfaces are controlled by the pilot, but in the few aircrafts that will not depend on the pilot. It will be automatically. It will be based on the pressure sensing or if the speed is variation is there. So based on that, the slats will be open and means extended or retracted. So as we can see here, some of the aircrafts, the slots are not controlled by the pilot, but operate automatically. Their movement is caused by the change of the pressure. As I told you, change of the pressure, which occur around the leading edge as the angle of, as the angle of attack increases. So at low angle of attack, the high pressure around the stagnation point keep in the slat in the closed position. So if we have a low angle of attack and we having high pressure, so this will be keep maintaining the stagnation point, because if stagnation point beyond that, the suppression will be flow suppression will be happening, and the amount of lift which we wanted is keep on reducing. So at high angle of attack, the stagnation point has moved underneath the leading edge, and suction pressure occur on the upper face of the slat. So these pressure cause the slat to move forward and create a slot. So change in pressure, change of speed, angle of attack. So this when it's happening, automatically the slats will be open or closed. So disadvantage of slat and slot. Till now we have seen the advantages. Now what are the disadvantages of slat and slot? So much higher angle of attack is required to benefit from the increased CL max for the use of slat and slat. So as we seen previously in the graph also, that if you require more than CL max value, so you have to get a more higher angle of attack. And visibility could hamper, which will affect the pilot and affect the landing of the plane. So visibility could hamper by increased nose up and nose up pitch, and landing could be difficult. So this is the disadvantage, which will create a problem for pilot. So drag and pitching movement, if we talk, means compared to the trailing edge devices, the drag and pitching movement are less. So we have seen it separate trailing edge, separate leading edge. Now here is a combine of both of these, the trailing plus leading edge devices. So most of the larger aircraft, like you can say the big Antonova 225 or the Boeing 787 Dreamliner or Airbus A380. So those kind of big jumbo aircrafts, they will be using combination of trailing edge plus leading edge both. So they have given a graph here over. You can see that the graph between coefficient of lift and angle of attack. So you can see that the first downwards they have given the basic section where the angle of attack and the coefficient of lift value was less. As you move on to the basic plus slot, the angle of attack value also increases, and the coefficient of lift value also increases. And if you go more to the flap plus slot, so there also you are getting the angle of attack values and the coefficient of values. So based on the requirement, based on the purpose, and based on the application, they can use this either trailing edge, either leading edge, or combination of both. So then the sequence operation, how will it work, which thing will open when, and how which one will be extended, which one will then retracted, and which flaps will open first, which slats will open first. So that the sequence will be there. So the sequence of operation is critical because I told that the change of variations of pressure, angle of attack, speed. So there are so many factors will come in that. Based on that, the performance of the aircraft, based on that, the sequence will be varying it. So lowering the trailing edge flap increases both upwash and downwash. So if you lowering means if you're opening the flaps, it will increase both upwash and downwash. So at high angle of attack, especially for large aircraft, the increased upwash could stall the airplane. Okay, so this is one problem. At the high angle of attack, especially for large aircraft, this will increase the upwash and stall the airplane. So if a stall condition happen, there the problem. If suppose pilot will not able to control it, then crash also can happen. So at the leading edge device, therefore he deployed before the trailing edge flaps is lower to take advantage of the ability of the leading edge flaps to increase the angle of attack for CL max. So what will happen if to avoid these things, what they will do, they will use the leading edge devices. Okay, so leading edge device therefore be deployed before the trailing edge flaps, because leading edge will be in the front of the wing and the trailing edge will be in the end of the wing. So, so they will do in that way, and they are lower to the take advantage of the ability of the leading edge and flaps to increase the angle of attack. So if the angle of attack increases, obviously CL will also increase, the lift value also will increase. So when the flaps are retracted, the trailing edge flap should be retracted first. So if they want to close it or they retract it, first they're going to close the trailing edge flaps. So as we see as an asymmetry of high lift devices. So what are symmetries and what are asymmetries? So deployment of high lift devices can cause large change in lift force. So as we have seen previously, different plane flaps, rudder flaps, and then then trailing edge flaps and leading edge flaps. So based on that, okay, based on the requirement, based on the application, we can use the high lift devices, which will definitely give where so much variation in lift forces. So asymmetry of deployment could cause a third roll control problem. So if we have not done the matching according which control surfaces will be open and which will be retracted, it will create a problem in rolling of the air. So a rudder might help in roll stability to some extent. So the rudder which is like at the tail of the aircraft, that can help in the roll stability of the aircraft, but up to some extent, not every time. So thus in modern aircrafts, the deflection of two sides is compared, and if it is eccentric, flaps movement will be prevented by automated systems. So this is the thing. If suppose there is a problem in deflection of two sides, so what they will do, they will use the automatic system flaps. So based on the flaps, based on the pressure, based on the speed of the aircraft, the slots and flaps will be open and close it. So here also one more thing is there, the flaps load relief systems. Okay, so this will be working automatically. So there the system is there called flap load relief systems. So large aircrafts, flaps are prevented to be deployed beyond certain high speed to prevent damage to the flaps. Yes, correct, because the flaps mostly are the extension of the wing parts, extension of the wing. So if the aircraft is flying at very high speed, then the extension part can be damaged. So to avoid that, they will not be opening at the high speed. And the flap load relief system will sense the flap load and prevent to the flaps deployment. So there is a system, flap load system. It will sense the thing, sensor will work and they sense the thing where they have to open, where not. If the speed of the aircraft is very high, they will not deploy them. They will not open that. They'll be given flaps deployment. If the flap selection is made, but the speed is too high, the flaps would be as soon as speed drops below. So what will happen if suppose they have selected to open the flaps, but the speed of the aircraft is too high. So what will happen is either the flaps will get be closed, either they try to reduce the speed of the aircraft and then they will open the flaps. Or if suppose flaps is got open, they try to reduce the speed of the aircraft. So that will not damage the flaps. Then choice of flap setting for takeoff of the aircraft, climb of the aircraft, and landing of the aircraft. So these are the you can say the task or the performance which aircraft will be doing it mostly in the takeoff conditions and climbing condition and landing condition. So most of the lift things we require over here. So first one you will see the takeoff. So lowest takeoff speed will be possible at large flaps deflection. So lowest takeoff speed will be possible at large flap deflection, but this gives large increase in drag as well, which will make the acceleration to take off speed difficult. So what will happen if the speed of the aircraft is less, the very big cargo aircraft is there, so it will take time to generate that much power and generate lift. So what will happen? They will be using the flaps to generate the more amount of lift. So that can be happen at lower speed. You can generate the lift and you can get takeoff, but it also increase drag as well, and it will make more acceleration to take off speed of the aircraft. Decision to take off speed difficult. So as a compromise is made and a lower flap setting is selected. So that's why what they have done, they will be using the lower flaps. Now come to the climb conditions. So climb gradient is reduced by flaps. Okay, so if climb gradient is limited, a lesser flap angle could be used to compensate, but the takeoff distance required will increase. So in climb condition also, they will be using the flaps, but what will happen is they will use the different flap angles, and to compensate for the takeoff distance required will increase. So what will happen? The more the length of the runway will be required for the takeoff purpose. So then come to the landing. So landing distance will depend on the touchdown speed. That is surely correct. And then the acceleration. So we have to reduce the speed of the aircrafts. We have to reduce lift. So most of the aircraft will be using a spoilers to reduce the speed of the aircraft. So to reduce the lift value, so they can touch down properly. So the lowest touchdown speed will be given by the highest CLmax obtained by large flap deflection. So this kind of things you can do it. So if the touchdown speed can be reduced very less, at the same time, the highest CL value, means coefficient of maximum value, can be obtained by deflecting large flaps. So large flap deflection will also give good drag, which helps in deceleration. Okay, so we require more drag compared to lift at the time of landing. We want to reduce the value of the lift, and we also want to reduce the speed of the aircraft. So this can be done as leading edge devices are also used to obtain ICL. So they can use the leading edge devices. We can see in the next figure. So as you can see here in the graph, the graph between the coefficient of lift and angle of attack, the left side and the right side coefficient of drag and angle of attack. So you can see that the angle is variation is there. So if the flaps up, how it is, and the flaps down, how it is. So you can see that at landing time, the angle is more, and the takeoff time, the angle is less. So which will avoid the stall. And if you see the right side graph, the graph between coefficient of drag and angle of attack, you can see that at the time of landing, the angle of attack is more, and the takeoff time, the angle of attack is less. So when the flaps is up, so this is the advantage. And then the management of high lift devices. So as you can see here, the graph between coefficient of lift and angle of attack. So as you can see that here a graph between coefficient of lift and angle of attack left side, and the right side is the graph between coefficient of lift and the coefficient of drag. So here you can see that in the figure the flap extended and flaps are retracted. So how the position and location will change based on the high lift devices. So if flaps is extending, so we can use at the two places, and the flap restricted we can use at one place, one point. And as you can see in the right side of the figure, the graph between coefficient of lift and coefficient of drag, the flaps retracted we can use at one position, and then flap extended we can use the two places. So here you can see the summary of my presentation. So high lift devices are used to lower the landing and takeoff speeds, and there are two types of high lift devices as we see in trailing edge and leading edge. And trailing edge flaps are plain, slot test bed, follower. We have seen the comparison and graphs. And the leading edge will be Kruger variable cambers. And the leading edge flaps are deployed before the trailing edge and retracted later than the trailing edge flaps. And the proper management of devices is very, very important. So I'm going to stop here, and thanks for joining the meeting. And I will see you in the next class.